A star collapses, but instead of forming a black hole, it becomes something far more bizarre. This is the Gravastar, a theoretical star trapped inside a bubble of mysterious dark energy. By the end of this journey, you will understand one of the most radical alternatives to a black hole ever conceived. We will explore how it could solve one of physics' greatest paradoxes and question if the universe truly permits infinite density. What does it mean for our reality if the cosmos refuses to create a true singularity? At its heart, a gravastar is a cosmic what-if. It is a hypothetical object, a theoretical answer to the troubling puzzle of the black hole's infinite core. Where a black hole is thought to crush matter into a point of infinite density, a gravastar offers a different, more structured fate. Picture not a bottomless pit, but a celestial onion with 3 distinct layers. Its core is not a crushing singularity, but a sphere of exotic material known as a Bose-Einstein condensate. Think of this as a kind of cosmic superfluid, a state of matter so calm and ordered that it behaves as a single, unified quantum entity. This strange core is then encased within a shell of incredible density, a crust made from the very matter of the original star, frozen just at the point of collapse. And finally, surrounding this entire structure is the most mysterious element of all, a bubble of dark energy. This dark energy exerts an outward pressure, a counterforce that perfectly balances the immense inward pull of gravity, preventing the final collapse into nothingness. It is like a perfectly sealed chocolate-covered cherry, where the hard chocolate shell holds a liquid center, or a single, stable bubble in a glass of soda that refuses to pop. This delicate balance of forces creates an object that looks like a black hole from the outside, but hides a radically different and far less destructive heart within. This perfect balance, however, solves a problem born from a far more terrifying idea. For decades, the black hole has been the undisputed king of cosmic monsters, a place where gravity wins so completely that it shatters the very rules of the universe. The trouble begins at its center, a point physicists call a singularity. This is not just a fancy word for something small. A singularity is a point of infinite density, a place where all the mass of a collapsed star is crushed into a volume of zero. Think of it like this: you have an entire mountain and you keep squeezing it, compressing it down to the size of a car, then a pebble, then a grain of sand. Now keep going, squeeze that entire mountain into a space infinitely smaller than an atom. The mathematics says this is what happens inside a black hole. But infinity is not a physical quantity, it is a mathematical warning sign. When our equations spit out infinity, they are essentially screaming that they no longer work. At the singularity, the reliable laws of general relativity, which govern the very large, collapse. The predictable rules of quantum mechanics, which govern the very small, also fail. It is a cosmic dead end for physics itself. This leads to an even more baffling puzzle, one that has kept scientists awake at night for half a century: the information paradox. Imagine you have a book, a detailed encyclopedia filled with immense knowledge. This book represents all the information about an object, everything from its atomic structure to its history. Now you throw this book into a fire. It seems destroyed, but in reality, the information is not truly lost. A physicist could, in theory, collect all the smoke and ashes and painstakingly reconstruct the exact book you burned. Information in our universe is always conserved. It might be scrambled beyond recognition, but it is never erased. Now take that same book and throw it into a black hole. According to our old understanding, the book crosses the event horizon and is gone forever. The information it contained simply vanishes from our universe, never to be recovered. This violates a fundamental tenet of quantum mechanics. The information paradox asks a simple, haunting question. Where does that information go? Does the universe simply forget? This is not just a philosophical debate. It strikes at the heart of whether reality is predictable and governed by consistent laws. A gravastar offers a beautiful way out. Because it has no true singularity, no point of infinite nothingness, the information about the matter that falls in is not necessarily destroyed. It could be preserved, scrambled perhaps, but still existing on the surface of that bizarre dark energy bubble or within its strange quantum core. This single idea transforms a cosmic shredder into a potential cosmic library, all by reimagining the heart of darkness. This radical solution did not emerge from the void. It was born from the minds of two physicists who dared to reimagine the impossible. In 2001, Paul Mazur and Emil Matola presented a theory that challenged the very definition of a black hole. Their motivation was clear and profound: to resolve the troubling singularity problem that plagued conventional models. They asked a simple yet revolutionary question. What if the collapse of a star did not end in a point of infinite density, but in a phase transition? This is the moment a substance changes its state, like water freezing into ice. Mazur and Matola proposed that at the very brink of becoming a black hole, the fabric of spacetime itself undergoes a similar, dramatic shift. Their work was a masterful blend of two great pillars of physics. They took the cosmic perspective of general relativity, which describes gravity, and fused it with concepts from quantum gravity, the quest to understand the forces that rule the subatomic world. A key ingredient in their recipe was the cosmological constant, a term Albert Einstein once introduced and later called his greatest blunder. This constant represents an inherent energy woven into the empty space of the universe, a repulsive force that drives cosmic expansion. Mazur and Matola brilliantly repurposed this idea, suggesting that this dark energy could manifest locally around a collapsing star, creating the stable, repulsive bubble that defines a gravastar. Their proposal was not a minor tweak to an existing idea, it was a full-scale paradigm shift. They painted a picture where the universe, faced with the logical absurdity of a singularity, simply changes the rules, forming a new and stable object that obeys the laws of physics rather than breaking them. It was an act of scientific innovation that offered an elegant escape from a cosmic dead end. This dark energy bubble is the ultimate guardian against the abyss. To understand its role, we first need to grasp the nature of dark energy itself. It is the most dominant force in our universe, accounting for a staggering 68% of all that exists. It is the mysterious pressure causing the cosmos to expand at an ever-increasing rate, pushing galaxies apart. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are the galaxies, and as the dough rises, every raisin moves farther away from every other raisin. Dark energy is the unseen force making that dough expand faster and faster. Now, Mazur and Matola proposed something extraordinary. They suggested that this cosmic force, which operates on the grandest of scales, could also manifest on a much smaller stellar scale. Within a gravastar, this dark energy is not spread thinly across the cosmos, but is concentrated into a perfect spherical shell surrounding the collapsed star. This shell creates a powerful, repulsive force that pushes outward with immense pressure. This outward push perfectly counteracts the inward crush of gravity, which is desperately trying to compress the star into a singularity. It is a cosmic standoff, a permanent state of balance. The result is a barrier, a cosmic shield that nothing, not even light, can truly penetrate from the outside. This is why a gravastar would look almost identical to a black hole to a distant observer. It possesses its own version of an event horizon, a point of no return. But here is the critical difference. In a true black hole, the event horizon is a one-way ticket to destruction. In a gravastar, this boundary is not a gateway to infinity, but the surface of this stable, dark energy bubble. It is the ultimate protective barrier, a force field that the universe itself erects to prevent its own laws from breaking. This single layer transforms a destructive monster into a stable, albeit bizarre, celestial object. Just inside that shimmering dark energy bubble lies a barrier of almost unimaginable density. This is the Gravastar's shell, a crust forged from the very remains of the collapsed star. While the dark energy pushes out, gravity has compressed this material into a layer of staggering thinness. Its width is measured in mere Planck lengths. To grasp that scale, know that a single Planck length is so minuscule that a proton is larger by a factor of 100 trillion, the entire mass of a star squeezed into a shell thinner than any known particle. This is not a shell of matter as we understand it. This is a crust of spacetime itself, warped and compressed into a solid-like state. It acts as the ultimate boundary, a physical horizon that is both a wall and a gravitational cliff. From our perspective outside, this shell defines the object we observe. It creates the point of no return, the event horizon that makes a gravastar appear identical to a black hole. Yet for anything crossing that threshold, the experience would be profoundly different. Instead of being torn apart by infinite tidal forces on a one-way trip to a singularity, an object would likely collide with this impossibly dense physical wall. The information it carried, its fundamental identity, would not be erased but potentially imprinted or transformed upon this ultimate surface. This solid shell resolves the paradox by providing a real, physical surface where the laws of physics still apply, a final frontier that stops the collapse and preserves the universe from the chaos of infinity. Deep within that protective shell, at the very heart of the Gravastar, lies its strangest secret. This is the core, a sphere of exotic material known as a Bose-Einstein condensate. To understand this, we must venture into the bizarre world of quantum physics. Under normal conditions, atoms are like a bustling crowd of individuals, each vibrating and moving with their own unique energy. But when matter is cooled to temperatures unimaginably close to absolute zero, a profound transformation occurs. The atoms begin to lose their individual identities, their distinct quantum states merging into one. They stop behaving like a crowd and start behaving like a single, giant superatom. This is a Bose-Einstein condensate, a fifth state of matter beyond solid, liquid, gas, or plasma. It is a cosmic superfluid, a substance so calm and ordered that it exhibits zero friction or viscosity. Within this core, the chaotic energy of a collapsed star is not crushed into infinity, but is instead frozen into a state of perfect quantum harmony. It becomes one coherent entity, a single wave of matter existing in a defined, finite space. This is the ultimate alternative to a black hole singularity. Where a singularity is a point of infinite density where physics breaks down, the Bose-Einstein condensate core is a finite, physical object governed by known quantum laws. It is the universe finding an elegant way to avoid its own mathematical nightmare, replacing a destructive paradox with a stable, albeit profoundly strange, reality. Imagine the difference between an endless, bottomless pit and a perfectly still, frozen lake. One represents chaos and the end of understanding, while the other, for all its mystery, is a real and structured thing. The Gravastar's heart is not a place of destruction, but a realm of ultimate quantum order. So, if you were an astronomer gazing at the heavens, how could you possibly tell them apart? From our distant vantage point, a Gravastar and a black hole would appear as nearly identical twins. Both would possess an immense gravitational pull, so powerful that they would warp the very fabric of space around them. Both would create a shadowy sphere, a point of no return from which no light can escape. Both would act as cosmic lenses, bending the path of starlight that passes too close in a phenomenon we call gravitational lensing. To any telescope, they would both present the same dark silhouette against the backdrop of the universe. The external behavior is a perfect mimic, a cosmic disguise that makes the Gravastar a brilliant theoretical impostor. Yet, beneath this identical surface, their hearts could not be more different. The first and most profound distinction is the singularity. A black hole is defined by its central point of infinite density, a place where the laws of physics cease to function. A gravastar, however, banishes this infinity entirely. Its core is not a destructive void but a structured object, a sphere of exotic quantum matter that remains finite and governed by physical law. This single difference resolves the terrifying information paradox, turning a potential cosmic shredder into a potential cosmic vault. The second critical difference lies in the nature of their boundaries. A black hole's event horizon is a one-way membrane, a mathematical surface you can cross but never return from. It is a gateway to the unknown. The gravastar's boundary, however, is not a true event horizon in that sense. It is a physical shell of unimaginable density, a solid wall of spacetime itself. Nothing passes through it to a singularity because there is no singularity to reach. Instead of an endless fall, anything encountering a gravastar would meet this ultimate surface. This solid crust acts as the universe's safeguard, a definitive barrier that halts collapse and preserves the integrity of physical law. The black hole represents a cosmic surrender to gravity's ultimate victory, while the gravastar represents the universe's stubborn refusal to break its own rules, creating a stable, if bizarre, alternative to the abyss. But this cosmic disguise is not necessarily perfect. The subtle differences in their internal structure could leave faint fingerprints on the universe, clues that astronomers are just learning how to read. One of the most promising ways to unmask a gravastar lies in the ripples of spacetime itself, gravitational waves. When two black holes spiral towards each other and finally merge, they create a specific, violent signature in these waves. It is a loud, chaotic crash followed by a rapid decay, like the ringing of a bell that is quickly muffled. A gravastar merger, however, might sound completely different. Because a gravastar possesses a solid shell and a bizarre quantum core, it would not simply swallow its partner. The collision would involve these incredibly dense physical surfaces slamming together. This could produce a much richer and more complex gravitational wave signal. Instead of a quick decay, the merged object might ring or vibrate for a longer time, its unique structure humming a distinct tune into the fabric of space. Listening to the universe with gravitational wave observatories is like developing a new sense, one that could eventually hear the difference between a true abyss and a dark energy bubble. Another clue might be found in the very shadows these objects cast. The Event Horizon Telescope made history by capturing the first image of a black hole's shadow, that dark circle surrounded by a fiery ring of light. A gravastar would also cast a shadow, but its details could be subtly unique. The nature of that dark circle, its precise size and sharpness, is governed by what happens at the very edge of the event horizon. Since a gravastar has a physical shell and not a true mathematical horizon, the behavior of light skimming that surface could be slightly different. It might create a shadow that is just a little less dark, or a ring of light that is marginally brighter or more structured. Discerning this would require observations of incredible precision, pushing our telescopes to their absolute limits. It is a search for a ghost of a difference, a single pixel in a cosmic image that could rewrite our understanding of reality. Finding that pixel would mean we are not looking into an infinite void, but at the surface of the universe's most exotic object. These subtle cosmic fingerprints are what gravitational wave observatories are now trained to detect. Facilities like LIGO and Virgo do not see the universe with light, they listen to it. Their massive laser arms act as hypersensitive microphones, picking up the faintest vibrations in spacetime caused by cataclysmic events millions of light years away. When two black holes spiral inward and merge, they create a very specific sound, a signature that has become familiar to scientists. It begins with a rising chirp as the objects orbit faster and faster, culminating in a final, violent crash. This is followed by a brief period known as the ring down, where the new, larger black hole settles into a stable shape, its surface wobbling like a struck bell. This ringing fades away quickly, muffled by the very nature of the event horizon. A Gravastar merger would tell a different story entirely. Instead of two objects with pure gravitational boundaries, you would have two entities with physical, solid shells. As these incredibly dense crusts spiral toward each other, they would not simply pass through an event horizon and vanish. They would interact, they would scrape and slam against one another. This violent contact between physical surfaces would inject far more complex vibrations into the fabric of space-time. The resulting ring down would not be a quick, clean decay. The unique structure of the merged Gravastar, with its dark energy bubble and quantum core, would continue to vibrate and oscillate. It would ring with a richer, more complex set of tones, and these echoes would persist for a noticeably longer time. It would be the difference between hearing a dull thud and hearing a crystal bell chime with a clear, lingering resonance. This distinct gravitational wave echo is a tangible, testable prediction. As our cosmic hearing becomes more acute, we might one day listen to a merger and realize we are not hearing a black hole at all, but the unique song of a star encased in a bubble of dark energy. This potential to hear the difference brings us back to the very reason the Gravastar was conceived, to solve a problem that threatens the foundation of physics. The black hole information paradox is not just a technical puzzle, it is a battle for the soul of reality. Our universe operates on a fundamental rule: information cannot be created or destroyed. It can change form, but it must always be conserved. Think of burning a wooden chair. The chair is gone, reduced to ash and smoke. Yet, in principle, if you could collect every single atom of soot and every wisp of gas, tracking their precise positions and energies, you could theoretically reverse the process and reconstruct the exact chair. The information about what made that chair unique was never truly lost. It was just transformed into an impossibly complex state. Now throw that same chair into a black hole. According to classical physics, the chair crosses the event horizon and is gone forever. Its information is shredded by the singularity and erased from our universe. This violates the core principle of quantum mechanics, creating a paradox where the rules of the very large and the very small are at war. A Gravastar offers a breathtakingly elegant escape from this dilemma. Because it has no true singularity, there is no cosmic shredder to destroy information. And because its event horizon is not a one-way mathematical surface but a physical shell of unimaginable density, information has a place to go. When matter falls onto a Gravastar, it does not vanish into an infinite pit. It collides with this ultimate crust. The information it carries, everything that defined that matter, could be imprinted or encoded onto this two-dimensional surface, much like a hologram. Alternatively, the information could be scrambled and preserved within the Gravastar's internal structure, perhaps within the strange, quantum-ordered core of Bose-Einstein condensate. In either case, the information is not erased, it is stored. The Gravastar transforms the concept of a black hole from a cosmic trash compactor into a potential cosmic hard drive. The information is locked away, perhaps forever beyond our practical reach, but it is not gone. The universe has not forgotten. This single idea resolves the paradox, suggesting that even in the face of gravitational collapse, the universe finds a way to obey its own most sacred laws, preserving the story of everything that ever was. This idea of information preservation leads to an even grander possibility, one that stretches the very meaning of reality. What if the dark energy core of a Gravastar is not just a stable object but a cosmic cradle? Some of the most daring theories in cosmology suggest that this bizarre interior could act as a seed for an entirely new universe. In this view, the death of a massive star in our cosmos might not be an end, but a beginning, giving birth to a separate reality in a process known as a budding baby universe. Imagine a single seed from a mighty oak tree falling to the ground. That tiny seed contains within it the entire blueprint for a new giant tree, a forest in potentia. It is a self-contained packet of possibility, separate from the parent tree yet born from it. A gravastar's core could be a cosmic seed. Its interior, a bubble of repulsive dark energy, possesses the exact kind of properties that physicists believe characterize the very birth of our own universe during the Big Bang. This dark energy bubble could undergo its own inflationary expansion, but instead of expanding into our space, it pinches off, creating a new, self-contained space-time continuum, forever disconnected from our own. The gravastar in our universe would appear as a black hole, a dark end point, but on the other side of that dark energy boundary, an entire new cosmos could be flowering into existence with its own laws of physics, its own stars, and perhaps its own potential for life. This transforms the gravastar from a mere alternative to a black hole into a potential link in an infinite chain of cosmic reproduction. Our entire universe in this breathtaking scenario could itself be the interior of a gravastar that formed in a parent universe, one branch on an endless, growing tree of realities. It is a thought that redefines both endings and beginnings, suggesting that within every apparent void, a new cosmos might be waiting to be born. This strange harmony of forces makes the gravastar more than just a cosmic oddity. It is a direct challenge to one of the greatest divides in modern physics. For nearly a century, two magnificent theories have described our universe, yet they refuse to speak the same language. Einstein's general relativity paints a breathtaking picture of gravity, not as a force, but as the graceful warping of spacetime itself. It predicts black holes and the bending of light with stunning accuracy. Meanwhile, quantum mechanics reveals the frantic, probabilistic dance of the subatomic world, where particles pop in and out of existence and reality is fundamentally uncertain. Both theories are brilliantly successful in their own domains, but they become mutually hostile when forced to meet. At the heart of a black hole, where the immense gravity of a massive object is compressed into a vanishingly small point, their conflict erupts into a full-scale war. General relativity demands a singularity, while quantum mechanics forbids the destruction of information that the singularity implies. The gravastar model steps directly into this battlefield. It is not just an idea born from general relativity, nor is it purely a quantum construct. It is a hybrid, a theoretical object that cannot exist without both. The dark energy bubble and the gravitational collapse are concepts from the cosmic scale of relativity, while the Bose-Einstein condensate core is a purely quantum phenomenon. The gravastar forces these two enemy theories to cooperate. It shows us a plausible, stable configuration where the warping of spacetime and the rules of the quantum world not only coexist but actively depend on one another to create a stable object. This is why gravastars are considered a quantum gravity object. They are a concrete, if speculative, blueprint for what the unified theory of everything might actually look like in practice. Instead of pages of abstract mathematics, the gravastar gives us a tangible picture, a celestial object that simply could not function unless the laws of the very large and the very small were finally reconciled. It is a glimpse into a future physics where the universe's two greatest stories are finally told as one. This elegant cosmic balance, however, has a potential flaw. The gravastar's very existence hinges on a perfect, unshakable stability between the outward push of dark energy and the inward crush of gravity. Many physicists argue this balance is impossibly fragile, a temporary state that would shatter in an instant. They contend that any tiny perturbation, a slight vibration or a bit of matter falling onto the shell, would upset this delicate equilibrium. The repulsive dark energy bubble might falter, or the dense crust might buckle, allowing gravity to finally win its long war. In this view, a gravastar would be a fleeting cosmic mirage, collapsing into the very black hole it was designed to avoid almost immediately after it formed. The debate centers on this knife's edge. For a gravastar to be a real, lasting object in our universe, it must withstand the chaotic environment of space for millions or even billions of years. It must survive the gravitational tug of nearby stars, the impact of cosmic dust, and the violent churn of its own formation. The conditions for such longevity are extraordinarily strict. The transition from collapsing star to stable gravastar would need to be incredibly smooth, a perfect phase change that leaves no room for instability. The dark energy bubble must form with exactly the right pressure, and the material shell must settle into a configuration of perfect uniformity and strength. Any flaw, any weak point in this cosmic armor would be exploited by gravity, leading to a catastrophic and final collapse. This is why the gravastar remains a topic of intense and active research. Scientists are not just asking if such an object can exist for a moment, but if the universe can forge one sturdy enough to last. They are running sophisticated computer simulations, modeling how these layers of exotic physics would interact under stress, searching for any possible configuration that could hold firm. The search is for a cosmic recipe so precise that it can turn a theoretical possibility into a stable celestial reality. Finding that recipe would mean the universe has a way to build a door that never opens, a permanent shield against the abyss. This unseen cosmic presence might hold the key to another great mystery, the true nature of dark matter. We know dark matter exists because its immense gravitational pull holds galaxies together, yet it emits no light and remains completely invisible to our telescopes. For decades, scientists have searched for the fundamental particle that makes up this hidden substance. But what if the answer is not a tiny particle, but a cosmic object? Gravastars, if they formed in the violent, dense conditions of the early universe, could be perfect candidates. Imagine the cosmos in its first frantic moments, a seething, hot soup of energy and matter. In that primordial chaos, pockets of space could have undergone the same phase transition that creates a gravastar, collapsing not from a star, but directly from the raw energy of the Big Bang itself. These primordial gravastars would then be frozen in time, drifting through the universe for billions of years. Their properties align almost perfectly with what we require of dark matter. They would possess enormous mass, creating the gravitational glue that binds galaxies. They would be completely dark, with their solid crust and dark energy bubble reflecting or absorbing any light that comes near. And they would be nearly impossible to detect directly, just like the dark matter we observe only through its gravitational effects. This idea transforms our search for the universe's missing mass from a hunt for invisible particles to a search for invisible, frozen stars. It suggests that the dark matter halo surrounding our own Milky Way might not be a cloud of exotic particles, but a vast swarm of these ancient, stable gravastars, each one a silent relic from the dawn of time. The feasibility of this idea hinges on that same question of stability. For gravastars to be dark matter, they must have survived from the earliest moments of the universe until today without collapsing into black holes. This is an immense challenge, requiring a level of perfection that pushes the limits of physics. Yet, if even a fraction of them endured, it would fundamentally reshape our cosmic senses. It would mean that a portion of the dark matter is not a form of matter at all, but a gravitational structure, a frozen moment of collapse preserved inside a bubble of dark energy. This possibility links two of the greatest puzzles in modern cosmology, the heart of a black hole and the nature of the unseen mass, into a single, breathtaking narrative. The death of a massive star begins this cosmic metamorphosis. As the star exhausts its nuclear fuel, its own immense weight triggers a catastrophic collapse. In a fraction of a second, the core implodes and a shockwave races outward, blasting the star's outer layers into space in a brilliant supernova. For a black hole, this is the end of the story, but for a gravastar, it is the moment of its strange birth. At the very precipice of forming a singularity, a phase transition occurs. the fabric of space-time itself undergoes a fundamental shift, like water instantly freezing. A bubble of repulsive dark energy blossoms at the core, halting the collapse. The remaining stellar material is frozen into an impossibly thin, dense shell just outside this bubble, while the very heart of the star transforms into that sphere of exotic quantum matter. In a cosmic instant, a destructive collapse is arrested, giving rise to a stable, structured object. Its life is one of profound and silent equilibrium. Once formed, a gravastar enters a phase of incredible stability, potentially lasting for trillions of years. It becomes a permanent fixture in the galaxy, a dark, massive object drifting through the void. Its existence is a constant, unseen battle, a perfect standoff between the inward crush of gravity and the outward push of the dark energy bubble. This balance is its defining feature, a state of suspended animation that defies the typical violence of cosmic evolution. It does not actively consume matter with the same ferocity as a black hole, for anything that falls upon its solid shell meets a definitive end, not an endless fall. It grows not by devouring, but by the slow, gradual accumulation of material onto its impermeable surface, adding layer upon microscopic layer to its already unimaginably dense crust over eons. Even this cosmic stability, however, may not be eternal. The ultimate fate of a gravastar hinges on that fragile balance of forces. One possibility is a slow quantum evaporation. Just as Stephen Hawking theorized that black holes can slowly radiate away their mass, a gravastar might also lose energy over phenomenal timescales. This Hawking radiation could, particle by particle, siphon mass away from its dark energy bubble and dense shell. Over periods longer than the current age of the universe, this process could cause the gravastar to slowly shrink, its dark energy pressure weakening until the balance is finally broken. It would not end in a violent explosion, but in a quiet fade, a final sigh as gravity at last overwhelms the failing repulsion, leading to a delayed but ultimate collapse into a true black hole. Another, more speculative death is transformation. What if the dark energy within its core is not perfectly stable? A slight fluctuation in this exotic energy could cause the internal bubble to begin expanding. Not slowly, but in a runaway process mirroring the birth of a universe. The gravastar's shell, that ultimate barrier, would be pushed outward with unimaginable force. From our perspective, the object would appear to swell, its gravitational shadow growing before it seemingly vanishes from our reality entirely. In this scenario, the gravastar does not die but gives birth. It pinches off from our spacetime, becoming the seed for a new, separate cosmos, a budding baby universe. Its death in our world is a birth in another, a cosmic passing of the torch where the end of one story is the beginning of everything else. This life cycle, from stellar collapse to either a slow fade or a transcendent rebirth, paints the gravastar not as a static oddity, but as a dynamic player in the grand, evolving drama of the cosmos. This elegant solution, however, requires us to gently bend one of science's most sacred pillars. Einstein's theory of general relativity is our most powerful description of gravity, a masterpiece that has passed every test thrown at it for a century. Yet its prediction of the singularity is its own undoing, a sign that even this brilliant framework has its limits when pushed to the absolute extreme. The gravastar concept does not discard Einstein's work, but asks if we might need to modify it in these most violent of cosmic environments. It suggests that under conditions of immense density, the equations of general relativity could receive a subtle, quantum-inspired correction. This is not about proving Einstein wrong, but about completing his picture, adding the brushstrokes that describe what happens when space and time are stretched to their breaking point. The gravastar is a specific example of a broader class of ideas known as gravitational vacuum stars, theoretical objects where the vacuum of space itself is not empty, but is filled with a structured energy that prevents total collapse. This idea fits into a grander theoretical pursuit, the quest for a theory of quantum gravity. For decades, physicists have sought to rewrite the rules of gravity at the smallest scales, to find equations that work for both the vast cosmos and the subatomic realm. Proposals like loop quantum gravity and string theory all attempt this unification, and many of them naturally do away with singularities, replacing them with a fundamental smallest possible volume or a bouncing behavior. The Gravastar is a tangible, physical manifestation of what that successful theory might predict. It gives us a concrete object to look for, a specific signature in the cosmos that would whisper, "Here, Einstein's rules are slightly different." It transforms an abstract mathematical quest into a potential astronomical discovery. Instead of a page of equations, we are given a candidate in the sky, a dark object that might be the experimental proof we need to see beyond general relativity and into the next great theory of everything. These cosmic possibilities have already begun to leak from scientific papers into the stories we tell. While the name Gravastar itself might not yet be famous, the concept of a stable, structured alternative to a black hole has ignited the imaginations of science fiction creators for decades. Think of the mysterious alien megastructures in films and novels, objects that are not quite black holes but something far more complex and intentional. A Gravastar, with its physical surface and potentially manipulable interior, offers a perfect scientific scaffold for such fiction. It transforms a destructive force of nature into a potential tool or even a home. An advanced civilization, one that has mastered the laws of quantum gravity, might not see a Gravastar as an end. They might see it as a beginning. They could, in theory, engineer such an object, stabilizing the dark energy bubble to create the ultimate fortress or an unimaginably powerful energy source. Its impermeable shell could shield an inner world from the entire outside universe, a perfect hiding place or a sanctuary lasting until the end of time. This leaps from the pages of astrophysics into the realm of narrative, providing a plausible reason for a hidden city of gods or a library containing all cosmic knowledge, safe within a shell that nothing can breach. The theoretical becomes a tangible stage for epic stories where the cosmos is not just a void to cross but a material to be shaped. This connection is a two-way street. The wild, speculative ideas of science fiction often prefigure the serious hypotheses of science. A writer dreaming up a stable black hole-like object for a plot decades ago was, in a way, laying the groundwork for the Gravastar concept. Fiction gives us a language and a visual palette for these bizarre ideas long before our mathematics can fully describe them. It allows us to explore the human consequences of such discoveries. What would it do to our society to learn that the terrifying black holes in our sky are not tombs but locked doors? What kind of beings would build such things? By playing with these concepts in stories, we are not just entertaining ourselves. We are conducting thought experiments on a cultural scale, preparing our minds for the day when our telescopes might finally show us that the universe is even stranger and more structured than we ever dared to believe. This search for cosmic fingerprints is driving a new generation of observatories, instruments designed not just to see the universe but to interrogate it. The next leap will come from space itself. The LISA mission, a space-based gravitational wave observatory, will open an entirely new window. Unlike its ground-based cousins, LISA will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, connected by lasers. This vast scale will allow it to hear the deepest, lowest frequency rumbles in spacetime, the kind produced by the mergers of supermassive objects. It is within these slow, cosmic chirps that the unique ring of a Gravastar might be most clearly heard. If 2 of these objects spiral together, LISA could capture the full, complex symphony of their collision, the prolonged vibrations of their dense shells and dark energy cores ringing with a clarity impossible to detect from Earth. Simultaneously, the Event Horizon Telescope is evolving from a single pioneering image into a global observatory with ever sharper vision. Adding new telescopes around the world and operating at even higher frequencies will allow it to capture black hole shadows with unprecedented detail. Scientists will scrutinize the precise darkness and sharpness of that shadowy circle, looking for the subtle but telltale signature of a physical surface. Is the edge of the shadow perfectly crisp as a true event horizon would demand, or is it slightly fuzzy, hinting at a solid crust of spacetime just beneath? A single anomalous pixel in a future image could be the clue that rewrites astrophysics, but the hunt is not confined to gravity and light. The very existence of a gravastar depends on the nature of dark energy and exotic quantum matter. Here, the search moves from the cosmic scale to the quantum realm. Advanced particle accelerators and experiments probing the properties of ultra-cold atoms are trying to recreate, in miniature, the conditions that might exist inside these theoretical objects. By studying the bizarre behavior of Bose-Einstein condensates and searching for any hints of repulsive vacuum energy in lab experiments, physicists are testing the building blocks of the Gravastar hypothesis. If we can understand how dark energy behaves on the smallest scales, or confirm the stability of the exotic matter theorized for its core, we move from speculative idea to plausible reality. The ultimate discovery may not come from a single observation, but from a convergence of clues, a whisper from Lisa, a blurred pixel from a telescope, and a breakthrough in a lab, all pointing to the same incredible conclusion, that the universe has found a way to build a door that never opens. The Gravastar is far from the only challenger to the classic black hole. Our map of cosmic possibilities is being redrawn by other equally radical ideas, each proposing a different fate for matter at the edge of oblivion. String theory, for instance, offers the fuzzball. This model banishes the empty, smooth spacetime of a black hole interior. Instead, it proposes that the entire region within the event horizon is a tangled, vibrating ball of fundamental strings, the tiny loops of energy that the theory suggests are the building blocks of reality. There is no singularity, no empty space, and no mysterious interior. The black hole is its own surface, a fuzzy, quantum-fluctuating entity where information is stored across its entire volume. It is the difference between an empty, echoing cave and a ball of yarn so densely wound that it has no center at all. Then there is the more violent firewall hypothesis, born directly from the information paradox. This idea suggests that the event horizon is not a gentle threshold one could cross unnoticed. Instead, it might be a blazing wall of high-energy particles, a literal ring of fire that would instantly incinerate any matter falling in. The firewall is a desperate solution, a proposal that the laws of quantum mechanics, in their need to preserve information, transform the point of no return into a destructive shield. This creates a new kind of paradox, pitting Einstein's principle of equivalence, which states a free-falling observer should feel nothing special at the horizon, against the unforgiving demands of quantum information theory. Each of these models, from the structured gravastar to the tangled fuzzball and the searing firewall, represents a different path in our quest to reconcile gravity with quantum mechanics. They are not just abstract speculations, they are competing narratives for how the universe handles its own most extreme conditions. This vibrant debate reveals a profound truth. The greatest monsters in our cosmos are not just objects to be found, but profound puzzles to be solved, and the final chapter on what lies within the shadow has not yet been written. These radical ideas are no longer confined to blackboards and supercomputers. The physics of a gravastar might be tested not in deep space, but in laboratories on Earth. Scientists are building analog systems, miniature cosmic experiments that recreate the most extreme physics in controlled environments. One of the most fascinating of these is the sonic black hole, often called a dumb hole. Imagine a river flowing faster and faster until the current moves quicker than the waves on its surface. If you were a fish in that river, you could swim easily downstream, but once you passed a certain point, no ripple you created could ever travel back upstream against the overpowering flow. The sound waves you make would be trapped just like light in a gravitational field. Researchers create this exact scenario not with water, but with a superfluid, often a Bose-Einstein condensate cooled to near absolute zero. By using lasers to stir this ultra-cold quantum fluid, they can create a flow where the speed of the fluid exceeds the speed of sound within it. This establishes an acoustic event horizon, a point of no return for sound. Any sound wave that crosses this boundary cannot escape. This laboratory setup becomes a stunningly accurate analog for studying the physics of real event horizons, including the potential for Hawking radiation, but for sound. The quantum fluctuations that occur at this sonic horizon can create pairs of phonons, the quantum particles of sound. One falls in while the other escapes, carrying energy away. This is the direct laboratory equivalent of the process that should cause black holes to evaporate. By studying these analog systems, physicists can probe questions central to the Gravastar model. What happens at the horizon itself? Is it a calm boundary, or is it a place of violent, energetic interaction? Could an analog system be manipulated to create a stable, sonic gravastar with a repulsive core that prevents the total collapse of the fluid? These experiments provide a tangible, testable sandbox for ideas that would otherwise remain purely mathematical. They allow us to play with the universe's most extreme rules in a tabletop experiment, offering clues about the true nature of the dark objects that dominate our galaxy. This resistance to the infinite forces us to reconsider the very nature of reality. If gravastars are real, they whisper a profound truth about the cosmos, that nature does not tolerate true infinities. The universe seems to have a deep-seated aversion to the mathematical absurdity of a singularity. It is not a place of ultimate simplicity where all rules break down, but a realm of immense complexity where it finds a more elaborate, structured, and finite answer. Instead of a dead end, it builds a door. This is a radical departure from the classical view of black holes as the final victory of gravity. It suggests that collapse does not lead to oblivion but to transformation. The cosmos, faced with a paradox, does not surrender, it innovates. It trades a destructive infinity for a stable, albeit bizarre, new state of matter. What does this tell us about the fabric of existence? It implies that reality itself may be fundamentally computational or informational at its core. A singularity is a place where information is lost, a cosmic crash that erases the data. A gravastar, by preserving information on its shell or within its core, upholds the principle that the universe is a system that never forgets. It keeps a perfect, if inaccessible, record. This moves the discussion from pure physics into the philosophy of science. For centuries, we have believed that deeper truths are simpler, that at the heart of every complex phenomenon lies an elegant, fundamental law. We chase a theory of everything hoping for a single, beautiful equation, but the gravastar presents a different possibility. The ultimate truth of nature might not be simplicity, but structured complexity. The most fundamental answer to gravitational collapse is not a zero, but an onion, a layered object requiring multiple branches of physics to describe. This challenges the limits of human knowledge itself. Our minds are wired to understand finite, tangible things. We grasp the very large and the very small by creating models, but these models are approximations. The gravastar is a signpost pointing to a reality that may always be just beyond our intuitive grasp, a universe that operates on principles of such profound complexity that we can only ever hope to glimpse their shadows. It humbles us, suggesting that the final answers are not simple, and that the cosmos reserves its deepest secrets for those willing to accept that infinity might just be a warning that we are asking the wrong question. This cosmic door, however, is not a gateway to other worlds. We must clear away the science fiction to see the science. A gravastar is not a wormhole. A wormhole is a hypothetical tunnel, a shortcut through the folded fabric of space-time that could connect two distant points in the universe or even link to different universes entirely. It is a passageway. A gravastar offers no such transit. Its interior is a self-contained reality, sealed off by that impossibly dense physical shell and the repulsive dark energy bubble. Nothing gets in, and certainly nothing gets out. There is no other side to emerge from. It is a destination, not a corridor. Similarly, it is not a time machine. The intense gravitational fields around black holes can cause severe time dilation, where time for an observer falling in would slow to a crawl relative to the outside universe. A gravastar would produce a similar effect from a distance, but this does not mean you could use it to travel to the future and back. The time dilation is a one-way ticket to the future for anything that gets close, not a controllable vehicle. You could not fly a ship around it and pop out in a different century, and this leads to the most critical clarification of all, the idea of entering one. Science fiction often paints black holes as risky but potentially traversable. A gravastar based on our current physics would be far worse. Remember that solid shell, a layer of space-time itself compressed to a width smaller than a proton but containing the mass of a star. Anything approaching that boundary would not experience a gentle crossing. It would collide. The energy released upon impact with that ultimate surface would be beyond comprehension, instantly transmuting any matter into a form we cannot even describe. It would be less like stepping through a door and more like hitting a wall at the speed of light, a wall made from the fundamental fabric of the cosmos. The gravastar solves a profound physics paradox, not by creating a safer black hole, but by replacing the infinite pit with an impenetrable vault. Its value lies in its stability and its ability to preserve the laws of physics, not in offering passage or sanctuary. It is a monument to cosmic structure, not an invitation for exploration. Ultimately, the gravastar matters because it transforms a cosmic curiosity into a tangible goal. Its true value is not merely in offering an alternative to a black hole, but in serving as a critical guidepost on the path to the greatest unsolved problem in physics, a complete theory of quantum gravity. For nearly a century, our understanding of the universe has been fractured. We have one set of rules for the immense force of gravity that sculpts galaxies, and a completely different, incompatible set of rules for the tiny quantum particles that build everything else. This division is not just an academic inconvenience, it is a fundamental crack in the foundation of our knowledge. The point of gravitational collapse, the very edge of a black hole or a gravastar, is the one place in the universe where these two worlds collide with absolute force. It is the ultimate laboratory, a natural experiment where the cosmic and the quantum are forced to interact. By studying what could happen there, by exploring possibilities like the gravastar, we are not just cataloging exotic objects. We are stress testing the very laws of nature. We are asking what must be true about reality for such a stable, finite object to exist. The answer to that question forces us to write new equations, to discover the missing principles that can finally unite the very large with the very small. This pursuit is not a niche interest for theorists. It is essential for a complete description of our universe. Without understanding this extreme frontier, our map of reality is fundamentally incomplete. The gravastar gives us a specific physical shape to look for, a potential signpost that reads, "The unified theory is here." Finding one, or even ruling it out, would provide the kind of hard, observational data that could steer decades of theoretical work, bringing us one step closer to seeing the universe not as two conflicting stories, but as one single, breathtaking narrative. From a dying star's final moments, we have journeyed to the edge of physics itself, exploring a cosmos that refuses to surrender to infinity. We have witnessed a star collapse not into a black hole's abyss, but transform into a gravastar, a celestial onion with a heart of quantum order, a crust of unimaginable density, and a protective bubble of dark energy. This radical object banishes the troubling singularity, offering a finite, structured reality where the laws of physics remain intact. It provides an elegant escape from the information paradox, turning a potential cosmic shredder into a cosmic library that preserves the story of everything that falls upon it. More than just a theoretical curiosity, the Gravastar challenges us to push the boundaries of our knowledge, serving as a tangible guidepost in the quest to unify Einstein's gravity with the quantum world. It represents the universe's own ingenious solution to a logical dead end, a testament to nature's preference for complex structure over destructive simplicity. The greatest discoveries in cosmology still lie ahead, hidden in the subtle echoes of gravitational waves and the faint shadows cast by dark objects. The next time you look up at the silent, starry sky, remember that the cosmos is filled with questions we have only just begun to ask, and that the most profound truths are waiting for the curious to